Okay, today we're going to talk about capacitors. We're going to segue from where we've been, which has been electrodynamics, to where we wish to go, which is circuits. And so today's lecture is to provide some of that transition. What is a capacitor? Well, a capacitor is a device used in electric circuits for charge storage. In fact, that's the idea of a capacitance, is its ability to store charge given a certain potential difference between its conductors. Frequency tuning, we'll see later on that the frequency will change what's called the impedance of a capacitor, and that will allow different frequencies to be resonated within an AC circuit, and by resonating you can in essence receive and amplify that signal from the general airwaves. So frequency tuning is a very important part used today to help tune in to signals in the general airwaves. Voltage control, capacitor stores charge but also stores voltage, and hence it can release that energy at a particular time, in particular for a macroscopic event such as trying to start a motor. You need a certain amount of energy once the motor is going to keep it going, but you need a larger surge of energy to get that motor started from its static state. And so a lot of times you see a large capacitor associated with motors so that you can charge up that large capacitor to give you that extra surge when you're trying to overcome its static state. So, what is capacitance? Capacitance of a device is its ability to measure or to store charge given a certain potential energy and a certain potential across its conductor plates. And we define it this way. Capacitance is equal to the charge divided by the potential. Charge divided by the voltage. So capacitance is how much charge can we get given a certain voltage. Generally, the capacitor will consist of two conductors oppositely charged, separated by an insulator, which we often call a dielectric. Insulators, dielectric, associated with the dielectric constant. The purpose of the insulator is to insulate between the two conductors so that there's no discharge, so they can hold more charge between those conductors. The unit of capacitance is the farad. A farad is equal to a coulomb per volt, named after Michael Faraday. Most capacitance are in the range of microfarads to picofarads, about 10 to the minus 6 to 10 to the minus 12. As we mentioned before, in a macroscopic sense, if you're trying to get a motor started, you might even get a capacitance up to about half a farad or something like that, because you need a lot of energy to get something macroscopic, mechanical like that to get going. But we're going to be dealing with circuits, and for our practical purposes, we're dealing with small capacitances involved in circuits. So we're in the range of microfarads to picofarads, really small capacitances. To illustrate this point, let's take a look first at what might be represented by a farad. Here's a farad. You can see has a general size associated with them. But like we say, that if we're dealing with circuits, we're dealing with values of capacitance that are much less than a farad. In fact, we might be dealing with something of the order of, say, a microfarad. This would be a microfarad, a little bit smaller, 10 to the minus 6 smaller. And if we're actually making measurements in the circuit, it may be a capacitance in the circuit might actually be like 2 microfarads. So This would be 2 microfarads. And for a lot of electronics, especially the smaller electronics, we might actually be working on the order of a picofarad. So there you have it. A farad for many macroscopic applications, but for circuits, we're dealing more with microfarads to picofarads. Basic strategy for general capacitance calculation. We are going to assume a charge of magnitude Q in oppositely charged conductors. Calculate the potential difference using techniques from chapter 25, and then use this formula, capacitance equals charge over potential difference, charge over voltage. For our purposes here in our transition, we're really only going to focus on 2 results, and that is one for the spherical capacitor and one for the parallel plate capacitor. So we're going to use this general method just for those 2 results, and you will be responsible for the results because we want to focus in on the circuit application. So we're going to do less of the derivation responsibility and more of the circuit applications. But here's the first result, or the first example. A spherical capacitor. A spherical capacitor consists of a spherical conducting shell of radius b and charge negative q that is concentric with a smaller conducting shell, sphere, of radius a and charge q. Find its capacitance. So we actually have 2 shells here. We have an inner shell with positive charge q of radius a, and we have an outer shell of negative charge q of radius b. Now we know from chapter 24, or just 2 chapters ago, that if you're inside a shell of charge, there is no electric field due to the charge on that shell, because if you apply Gauss's law arbitrarily close to that shell, you would enclose no charge due to that shell. Hence, there would be no field. It acts like a Faraday cage. And if you're outside the shell, then the electric field would act just like a point charge due to the charge on that shell that is within your radius. So that's what we have here. We have 2 shells, but the electric field between them is actually only going to be due to the charge on this first shell, this inner shell. From chapter 25, we know that the potential difference should be the negative integral from radius A to radius B of the electric field, dr. But that electric field is really only due to this inner shell, which acts like a point charge from the center. So that's going to be kq over r squared between the plates. K being our famous electric constant, 9 times 10 to the 9. We'll pull that out. So we have the integral from A to B of dr over r squared, and you know that to be 1 over r. Evaluate from radius A to radius B. So we have 1 over b minus 1 over a. Let's find a common denominator for these fractions. So we'll multiply them both by 1, and we get this nice result. That the potential difference between these 2 shells is equal to k times q times radius a minus radius b over radius a times radius b. So b is greater than a, then the magnitude of this potential in a positive sense would be equal to kq b minus a over a times b. But we want to find the capacitance. Capacitance by definition is the charge divided by the potential difference. So that's going to be q over this. The q's are going to cancel out, and the fractions are going to reverse. So we're going to have the capacitance is equal to radius a times radius b over k, our famous k constant, times b minus a. And that is the capacitance of concentric spheres. What is nice about this result, what is beautiful about this result, is that this capacitance is only dependent on geometrical values. K is just a constant, 9 times 10 to the 9, but the other values, radius A, radius B, are the geometrical aspects of our inner and outer shells. And so the actual charge doesn't come into play, and the actual voltage doesn't come into play when we get to this result. It's just geometrical factors. If I had a factory, I could make this capacitor just by making these shells and putting this device together. And neat. What would be the capacitance of an isolated spherical conductor? Well, let's use this last result that we just had for for consecutive spheres. Well, let's take that outer sphere and let's move it all the way to infinity. Move it all the way out, so we basically isolate the inner sphere by itself. Here's our capacitance for that spherical conductor, or spherical capacitor, sorry. What we're going to do is we're going to move B out to infinity. We're going to make B infinitely large. Hence, B minus A is also going to be infinitely large. A is going to be insignificant compared to B because B is going to be infinitely large. So we'll end up basically with B over B, which will cancel out. And so as radius B goes to infinity, our capacitance will approach radius A divided by K. Or since K is 1 over 4 pi epsilon naught, this will be 4 pi epsilon naught times A. This is the result I want you to take note of. So this is the capacitance of an isolated sphere. It's simply the radius of the sphere divided by K. Nice. Let's try this out. Here's a problem from the book. Find the capacitance of the Earth. Let's treat the Earth as this sphere, this spherical shell of charge. Treating the Earth as a sphere, radius 6.37 times 10 to the 6 meters. The capacitance of the Earth is the radius of the Earth divided by our famous K constant. 6.37 times 10 to the 6 meters divided by 9 times 10 to the 9 equals 7.08 times 10 to the minus 4 barids. That is the capacitance of the Earth. Seems a lot smaller than you might expect, but there is a pretty large sphere as it is. All right, let's do this example. So our first result is a capacitance of an isolated sphere. That's the one that I want you to take note of. That capacitance is equal to the radius of the sphere divided by K, 9 times 10 to the 9. Our second major example is the parallel plate capacitor. This is one that we're going to use a lot. We know from chapters 23 and 24 that if you had an infinite sheet of charge, in this case a positive infinite sheet of charge, you'll have an E field emanating straight out, normally out from that infinite sheet, and the value of that electric field will be equal to the surface charge density sigma divided by 2 epsilon naught. We proved that in chapter 24. So, and the E field is constant. It's independent of your distance from that infinite sheet of charge. So it's just a constant, the surface charge density divided by 2 epsilon naught. If I brought in another sheet, this one oppositely charged, negatively charged, then I would have the same magnitude electric field, surface charge density over 2 epsilon naught, But if it's negatively charged, then that electric field will be going into it, normally into it. So that if these two sheets of charge were near each other, then we'd actually have, by superposition, two electric fields that we could add, because they're both in the same direction, in between these two sheets. And hence we would end up with an electric field that was the combination of those individual electric fields. In other words, the electric field between these two sheets of charge will be equal to E1 plus E2, which is equal to sigma over epsilon naught. In other words, 1/2 sigma over epsilon naught plus 1/2 sigma over epsilon naught gives us sigma over epsilon naught. And that is the electric field between these two planes. Well, the voltage then, since this is a constant electric field, we could calculate the potential difference between these plates. And from the previous chapter, we know that the potential difference would just be at least a magnitude, the field times the distance between the plates. And hence, our voltage difference between these plates is it has a magnitude of surface charge density over epsilon naught field times d, where d is the distance, separation distance between the plates. So, if we use the definition of capacitance, which is the charge over the potential difference, we now have the charge, which is the total charge of the plate, which would be the surface charge density times the area of the plate, sigma times A, over the potential difference, which we just found to be sigma over epsilon naught times D. The surface charge densities cancel out, and with a little bit of rearranging, we have that the capacitance is equal to the permittivity of free space, epsilon naught, times the area of one plate divided by the separation distance, d. This is a parallel plate capacitance, where two parallel plates separate by nothing, or air. Where A is the area of one plate, D is the separation distance between the plates, and epsilon naught is 8.85 times 10 minus 12 coulomb squared per Newton meter squared, universal constant. Like the spherical capacitor, this is rather beautiful in the sense that this capacitance, again, is only dependent on geometrical factors. Epsilon naught is a universal constant. A is the area of one plate. D is the separation distance between the plates. So I can construct this thing basically in a factory based on the area of the plate and the separation distance, and I would have some idea what that capacitance should be regardless of the actual charge or voltage used on it. At least that's what this is saying. Let's try out an example. A parallel plate capacitor has an area of 2 square centimeters, which is equal to 2 times 10 to the minus 4 square meters, and a plate separation of 1 millimeter, 1 times 10 to the minus 3 meters. Find its capacitance. Well, from the previous formula, that should be equal to epsilon naught times the area of one plate divided by d. 8.85 times 10 to the minus 12 times the area of one plate, which was 2 square centimeters, or 2 times 10 to the minus 4 square meters, over 1 millimeter, which is 10 to the minus 3 meters. That gives us 1.77 times 10 to the minus 12 farads, or 1.77 picofarads. All this is if I had two plates, two conducting plates, separated by either air or a vacuum. What would happen if I actually put an insulator between the plates? And here's an air-filled capacitance. But if I actually put an insulator between the plates, what that would do is that it would allow me to actually put more charge on the plates given a certain voltage, because I would ensure a little bit better that the plates would not discharge between the two of them. In other words, by putting an insulator in there, I increase its ability, its capacitance, to hold charge given a certain voltage. And the material we put in there is some insulator that has not a permittivity of epsilon naught, but a permittivity of epsilon. So our capacitance is now epsilon times the area of one plate divided by the separation distance d. But one way we could write epsilon, the permittivity of that material, is some constant times the permittivity of free space. So we're going to rewrite this epsilon as some constant, kappa or k if you wish, times epsilon naught, times the area of one plate over the separation distance d. This constant, this kappa or k, is called the dielectric constant of that insulator, of that material. So, with this new method then, by putting an insulator in between the plates, we actually increase the capacitance by some factor, and the factor we increase it by is this dielectric constant. Here are some common dielectric constants. Vacuum is 1.000000000. Air is 1.00059, so basically it's almost the same as vacuum as for all practical purposes. So those dielectric constants do not increase the permittivity beyond the permittivity of free space, which they shouldn't. Paper, on the other hand, is 3.7. So if I take those two plates and I stuff paper in there, I can increase its capacitance, its ability to hold charge given a voltage, by a factor of 3.7. Amazingly, water is 80. You probably don't want to use water for other reasons, because it may have ions and electrical conductivity by that. But water has a dielectric constant of 80. Strontium titanate is 233. So if I put strontium titanate between the plates, I can increase the capacitance by a factor of 233. And that sounds like a good thing to do. So let's try this out. Here's another example. A parallel plate capacitor has plates of dimensions 2 centimeters by 3 centimeters, separated by 1 millimeter thickness of paper. Dielectric constant for paper is 3.7. Find the capacitance of this device. Well, that's equal to dielectric constant, epsilon naught, area over separation distance. 3.7 dielectric constant for paper. Permittivity of free space, epsilon naught, is 8.85 times 10 minus 12. The area of this plate is 2 centimeters by 3 centimeters, or 6 times 10 to the minus 4 square meters, over 1 millimeter gives us 20 times 10 to the minus 12 farads, or 20 picofarads. So, the main results for this very short lecture is the capacitance for an isolated sphere, which is the radius of the sphere divided by our famous K constant, 9 times 10 to the 9. And this last result, which incorporates all of our parallel plate possibilities, or basic possibilities, which is the dielectric constant kappa times epsilon naught over the area divided by the separation distance d. Those two results are the ones I want you to take note of as we transition from electrodynamics into circuits.